Okay, so yes, I think we can start now. I think we spent last probably 7 lectures in the last 4 weeks uh, discussing in detail different thermodynamic aspects of this topic, right? So we first introduced the microscopic states based on which we describe the introduce the phase space and define the entropy. And then we move on to define free energy and demonstrate that how we can compute these quantities using some very useful but ideal model systems like ideal solution, regular solution, right? And from the insights of the free energy analysis, we go ahead and construct the phase diagram. And we show that you can basically represent a lot of useful information on the phase diagram. And then we analyze different type of phase diagrams to show that how can we go back and extract such information. And we show some phase diagram of more complex engineering system. But all of these are kind of fundamentals for our discussion of phase transition, because you have to first know what are the driving forces which are determined by the free energy, right? We know how to compare the stability of two phases at the same temperature. Whichever has the lower free energy going to be the stable phase, and the difference of the free energy is literally the driving force, thermodynamic driving force that going to lead to the phase transformation. And we know that at a given condition, including temperature and composition, which phase exists in the system, what are their composition, what are the amounts of each phase, and what the microstructure looks like. So all of these are thermodynamic aspect concerning phase transformation. Okay, so starting from today, we're going to switch gear and begins to talk about another very important tool we're going to use a lot in our subsequent study of phase transformation, namely the diffusion, which is the key kinetic aspect or kinetic mechanism that allow the phase transformation to occur, especially in alloy. Okay, because typically, as we already see from the phase diagram, if you initially have a solid solution with a single composition, right? When this solid solution separated into 2 different phases, either through precipitation or even eutectic, you need to, the composition of the two resulting phases will typically be quite different from the initial solid solution, right? And this is achieved by diffusion of the solutes. So in the next few lectures, we're going to focus on this particular kinetics diffusion, in particular in solid material. Okay, so that's going to be what we'll be focusing on. So yeah, so today this is kind of introductory lecture about diffusion. I think most of the topic we're going to introduce today, you already probably seen them before. So we're going to talk about interstitial diffusion. This is probably the most simple type of diffusion in solid state. And using this background, keeping the solid interstitial diffusion in mind, we're going to use this mechanism to derive the so-called Fick's first law, which you definitely have seen this before in different contexts. And then we define diffusivity, and using the conservation of solutes, we're going to derive the Fick's second law, and combining the first and the second law, we'll derive the diffusion equation. So, but again, in the context of the solid solution, you may have seen these mathematical derivations, but we're focusing more on how you can assign a physical interpretation of these mathematical law in the solid material. So that's going to be the focus. But overall, I think this wouldn't be quite difficult. Okay, so but before we talk about solid state solution, let's just go back to our intuition and think what we already know about diffusion as a phenomenon, right? So here I give a very simple example. Suppose I have a drop of this a red ink, and then I just put a few drops of red ink in the tank of water. Initially you're going to see a big blob of red droplet in the water, right? But if you're patient enough and wait sufficient long time, eventually you'll see that this very dark red droplet gonna become more and more pinkish, and eventually instead of having a cluster of these red ink molecule, these red ink molecules going to be uniformly distributed within this tank of water, and you will see it's kind of a very uniform, homogeneous mixture of pink liquid. Okay, so this is, and the way that how these red droplet molecule redistribute themselves from this clustering state to a very uniform distribution state This process is called diffusion. Now, this is we call this diffusion, assuming that you can wait patiently enough so you're not disturbing this water. If you put a stick in the water and stir it, that's not diffusion, that's convection. Okay, we just wait for the atom to move around, for the molecules to move around in their own way, and you achieve this homogeneous state, and that process is diffusion. And the mechanism for this diffusion is also well known. This is kind of the due to the Brownian motion of large molecules. So what we show here is a simulation showing that you have a large yellow particle, which are constantly being collided by the smaller black molecules in the original liquid. And then overall, what you see or observe as the motion for this yellow particle is a kind of random motion. We call this Brownian motion, or we call this diffusion of the yellow particle. Okay, so I think this is what we already know about diffusion. And there are several interesting things about this particular phenomenon. One thing is that, although if you keep track of the exact location of this yellow particle at each point of time, you can have a trajectory, which are typically very random. And this trajectory, if you do this for a long time, you see a lot of intersections can intersect with itself. And even if you start with exactly the same particle at the same location, which I can show here. In here, I replaced the yellow particle with the red particle, but I placed the particle initially in the middle of the box, and I didn't show all of the smaller, molecule for the background here. I just focus on the red one. And what I show as the blue are the trajectory of the particle, as if I can follow the evolution of this particle trajectory for a very, very long time. So you'll see something like that. And even each time you start from exactly the same location, due to the intrinsic randomness in this particular processes, because you cannot control at each time point which black, original small molecule going to collide with this red one. So at each particular time point, it's going to be a random processes. So even you start from the same exact location with the same type of initial condition you can prepare for this large particle, you can still end up with completely different types of trajectory if you try to repeat the experiments. So this also, so basically this allows us to rethink about what is the best way of describing this type of motion, right? So if you just follow the normal way, consider this to be a Newtonian dynamics, which it is true, but you're going to get these, kind of random trajectory, which does not quite make sense or not necessary, right? Because in most cases, what we're interested in for these systems are not exact trajectory of a particle, right? Because most times these are just, microscopic systems, and we do not have the time and effort, and in most cases, we don't have the tools to exactly keep track of the location of the particle at each time point. What the best we can do is that at initial point, we can take a SEM image of this atomic system. And then after a certain time t, which are typically much larger than the time required for the particle to do this very jiggling random motion, right? After a few seconds, even a few seconds, from our perspective, the particles have been doing a lot of motions during this very short period of time, because the typical relaxation time for them are probably milliseconds or even smaller. So what we're going to end up is seeing that initially we see the particle here, but after some time, it may jump to this position. So we don't see all of the details of this zigzag motion, right? So that is the best we can do in terms of observation. And based on this fact, and also the fact that the trajectory is mostly random and we do not need to get a lot of information out of this, the way that we describe the motion of diffusion particle is typically by averaging over all these trajectories. So instead of having a precise description of the location along each particular trajectory, we take a statistical approach of describing these systems, right? Instead of knowing exactly location of each time point for a particular particle, we do the experiments many times, and we collect all the positions of all the time that we can collect the data. So if we collect all those points, you're going to see something like that. Okay, so this typically means that, okay, if I start from the middle of the box, allow the particle to diffuse around over a certain period of time, t, okay, I have the probability of finding this particular particle at a certain position. Now, this is what we use to describe diffusion. Instead of describing the exact location as we did for Newtonian dynamics, okay, we use this particular stochastic way to describe the diffusion. And in this sense, it's reasonable to introduce an average distance that traveled by this diffusive particle over time t. Okay, and that distance is given by this equation. Okay, we will show this later, but I think this is something we already know. Typically, we call this the diffusion distance, right? And t is the time that it takes for the particles to diffuse around. And x, okay, is not the length of trajectory it travels. It's simply the distance between the initial position of the particle and the final position of the particle that you make observation during time t. Okay, so this is not the length of the trajectory. It's simply the distance between the initial and the final position of the particle during time t. Okay, and d is the so-called diffusivity or diffusion coefficient. It can be interpreted as the rate of motion in a similar role of velocity. Okay, but a key difference that you can see here, if you're doing this ballistic motion, okay, the distance traveled by the particle is proportional to time. Okay, but here it's proportional to the square root of time. Yes.
Professor, what's the medium?
The medium, what do you mean by medium? You mean what is
Where are they
exact?
moving?
You can consider they're moving in a liquid of any kind, maybe water or some organic, liquid. Doesn't really matter. This wouldn't change the physics of the system. The only thing changed is going to be the diffusion coefficient, but this general mathematical law will not be changing. So the details of the molecular details of what exact system we're looking at is not important. Okay, so that is basically a recap of what we know about diffusion, like in the liquid state or in the normal way, right? The Brownian motion, diffusivity, and diffusion distance, and the stochastic way that how we describe this quite different dynamics, right? We call this the diffusive dynamics to distinguish from the ballistic dynamics that you basically work with for any football, a car that follows Newton's law of motion. And the key here is to realize we're using a stochastic way to describe on average, how far the particle can move around, but not exact location, or the trajectory of the particle. Okay, so now how this picture will change in the case of solid state. Okay, so in here I have some very simple example or animation showing the diffusion of different type of particles in a solid material. Okay, so clearly I think you can see at least two type of particles, right? What typically do you call this red guy from a material science class? What do you call this red guy?
Interstitial impurity.
This is typically called interstitial defect, or right, interstitial particle, right? So you can see that this particle can move around in the system. Again, this is highly schematic, but at least you see that it can hop from one possible location to another possible location and doing this random hopping, right? And also an interesting fact is that although it's schematic, but you can see as it does this random hopping, it has to squeeze through between a pair of densely packed blue particles, right? So this means that typically when you do the hopping, you will need some activation energy. Okay, so what is this type of guy? What do you call this guy? Which is gone here. But if you have this,
Vacancy.
this is a vacancy, right? And although this vacancy is not a real particle, but if you imagine that I have an imaginary particle, you can see there the vacancy is also diffusing around. At some point, it sees the interstitial, and the interstitial jump into the vacancy. Okay, but anyway, so the whole point to show here is that you still have diffusion, right? Because if you look at the way how they move around, it's pretty much random, right? So this is what we call the solid state diffusion, okay? Because in a real material, you always have, especially in the alloy, you always have these different type of point defects. And these point defects at finite temperature, they're allowed to move. And the way how they move around is through diffusion. And as you can probably imagine, if I increase temperature, their motion is going to be more and more active, right? So this is quite useful because in phase transformation, we want these solutes. You can imagine that these red interstitials are solutes like carbon in a steel, right? They can move around in the system so that at a given temperature and proper conditions, you can induce different type of phases, due to the diffusion of these guys. Okay, so that's basically a picture for a very, again, schematic picture for solid state diffusion. And we're going to talk about each type of diffusion in detail, right? We're going to talk about interstitial diffusion, vacancy diffusion, and even self-diffusion. Okay, now what is self-diffusion? If you look at this guy, right? So there's a particle that can move into the vacancy site. Okay, that is called self-diffusion. And self-diffusion is always due to the vacancy diffusion. So we're going to describe all these type of diffusion in solid state in detail. But here it's just to give you a very rough intuitive picture of what's going on. So now let's start with interstitial diffusion, which is the easiest way to treat because this wouldn't change the underlying lattice, right? So this is the most simple analog to the liquid state diffusion. And now what I show here is I think I will not say this is a better illustration, but I think it illustrates another aspect of diffusion, of interstitial diffusion. Okay, so what you can see here is that we focus mainly on the white particles or silver particles, which are the interstitials. They're diffusing in lattices of a set of blue particles. Okay, now one thing you can see here is that these white particles, they're vibrating all the time, right? And at some point, the vibration can be suddenly get stronger, probably to receive a phonon from the environment. Okay, so it gets stronger, and so it, this allows the particle, the white particle, to hop over, between a tightly packed pair of blue particles, like these two guys, right? I cannot follow exactly where it's going, but for this guy, you see that it hops from this place to this place. It's because it's vibrating all the time, and at some point the vibration can be very strong enough so that it can squeeze through the tightly packed pair of blue particles and hop into different pockets. Okay, so this is basically illustrates the mechanism for interstitial diffusion. Namely, at any finite temperature, all the particles are going to be vibrating, right? And both the blue interstitial, both the original lattice particles on the lattice, which I'm not showing the vibration, but you can imagine they're still vibrating. But because probably they're heavier, so the vibration may be not as stronger as the one for the white ones. Typically, the interstitials are lighter, smaller particles, so the vibration is stronger. At some particular point, this guy may receive a fluctuation in terms of thermal energy, right? And this is going to increase the fluctuation, the vibration, such that this vibration can give this guy sufficient kinetic energy to squeeze through the barrier, imposed by these pair of blue particles, and this, and through this way they're making these random hops, right? But this also illustrates the key mechanism for interstitial diffusion are random hopping, right? Because there's no particular direction that this guy wants to go. It can go to any direction, right? But I'll ask you a question later why, in this particular case, effectively you'll see that all of the particles are effectively moving from left to the right. But if you look at a single particle, suppose there's no other neighbors around, right? There's equal probability for this guy to hop into any of the possible nearby paths, right, for this guy. So that is, very intuitive understanding of diffusion, of the solid state diffusion, in particular in the case of interstitial diffusion. And now we're going to take all of the situation. I hope that we are on the same footing. We're going to take all of these situation and do some very interesting mathematics to see how we can arrive at the same mathematics, as we already seen for the liquid state diffusion. Okay, so now we're gonna take that very nice image and that very nice animation in mind, but now we're gonna look at some more rigorous boring plots. Okay, so this is a similar picture that you have seen before, but it's static, of course, right? So we consider that you have a crystal structure formed by these large white particles. You can consider these are ions, and then I have small black particles. You can consider these are carbon, right? They're taking the interstitial. Again, this is a schematic plot, so I'm going to just show you a two-dimensional plot, and it's in a very simple square lattice. But again, this is just for demonstration. Okay, you can work out the more detailed mathematics for any three-dimensional lattice with the more realistic packing structure of the atom. Okay, so now the diffusion that we're interested in is basically a transport of the atom, right? So because the atoms are hopping around, so for example, you can take any of the atom, at this time, it basically located at this particular site, but at a later time, they can hop into any of the possible, pockets available to this particular atom, right? Now, if we consider that this is a three-dimensional lattice, right? And we have a cubic system, okay? It's a three-dimensional lattice and it's a cubic system. How many different possibilities, how many different available paths that this particular interstitial atom can have? If this is one-dimensional system, how many different positions this atom can go?
12.
This is a cubic system in general, right? So if this is one-dimensional, it can only go to, where's my mouse? can go in this way or this way, right? For one-dimensional system, this guy can go either back and go forward, right? There's two possible choices. And then, but if you look at this, okay, because we have a cubic system, so each of the three principal directions are equivalent, right? Because for each direction, you have two possibilities. Now you have three directions. So you have 6 possibilities that you can go, right? 2 possibilities for each direction. So now I'm only picking a particular direction. So now I'm interested in the transfer or transport of the black atom only from left to the right. If I only pick, only focus on the transport from this guy to here, okay? From this to here. And then I define an imaginary plane, which is highlighted by this very dark blue dashed line. What I'm interested in is that per unit time, okay, and per unit area, how many black atoms are hopping from this particular plane 1 onto plane 2 from left to right. Okay, I'm interested in this. And this effectively defines a directional flux, right? So this, which is particularly given by this, okay? So this basically, this is a flux, right? And this flux gives you per unit time and per unit area, how many black atoms originally at this plane 1 hop through this imaginary plane, which I highlighted by the dark dashed line, onto plane 2. Okay, so this is what we define by the flux from left to the right of this atom. And this is 1/6 times the gamma. This is the vibration frequency, the hopping rate. In this particular case, the hopping rate. Per unit time, how many hops the atoms will be doing, right? And then this is the number density of the atoms on this plane. Okay, so this is number of atoms. N1 is number of atoms on plane 1, okay, per unit area. And the hopping rate is given in terms of number of hops the atoms doing per unit second, okay, per unit time. And 1/6, this factor takes into account that you have 6 possible directions you can go in the cubic system, and we only choose one particular direction. Okay, so this is the flux, particularly to atoms that hopping from the plane 1 to plane 2 per unit time, per unit area.
So I have a question here. So the gamma point, the gamma B, that should be the function of the material, right? The solvent material, the major component of the alloy.
Yes, and it's also a function of temperature in general. But in here, we consider it a constant.
Yeah, but it should, it should depend on the material also through which the atoms are diffusing, right?
It depends on the material. It depends on the atoms diffusing. Yes, we'll derive this in more detail. But for now, just think this is a constant.
Okay, thank you.
No problem. So now the question for you is that, is this the overall flux for B atom from left to the right? We definitely, this is definitely an important contribution to the flux, right? The flux, as we define, is the number of atoms, going through this imaginary plane per unit time, per unit area, okay, from left to the right. Now we work out one particular important contribution, because we know if we're interested in atom transferring from right to the left to the right, this will be definitely an important contribution. But is this the only contribution?
If there is place for them to go, it should also, that factor should also come, right? If we have like sites where they can go.
Yes.
If they're all already filled.
So the
concentration.
So the point here is that this takes into account the atoms that initially at plane 1 and hop onto plane 2, right? But the point to ask is that, is there any atom that's going to contribute in the opposite direction? Because you're going to kind of counterflux, right? There's a possibility that originally there are atoms already on plane 2, but there's a probability for these atoms to hop back onto plane 1. Now this is going to cancel some of the flux you basically computed here, right? And it contributes to overall flux from left to the right. So that was I'm asking. So in order to compute the overall flux, right, you have to consider the hopping from 1 to 2 and also the hopping from 2 to 1, because they're all happening all the time, right? This is there equal probability that these things are happening. Now the only difference that you see for the counterflux from right to the left is that the number of atoms that can possibly hop back is given by now the the density of the atom on this particular plane, right? N2 is the number of atoms on plane 2 per unit area. And this gamma B, again, is the hopping rate, is given by number of hops that each particular atom can do, is given by the unit for this is this per second. Okay, so this is a counterflux, right? So you have contribution both from the left to the right and from the right to the left. So the overall flux, okay, is basically given by considering both these two effects together. Okay, so it's simply given, because we're now defining the direction from left to the right to be my positive direction, right? So this counterflux should have a negative sign because it's going back, right? So we have this negative sign associated with N2, but the prefactor are the same. And then basically this gives us the overall flux of atom B, from left to the right. And again, flux is defined as number of atoms that the transport from left to the right per unit area per unit time. Okay, so this is the first thing we derive. Okay, this is the atomic flux. Okay, and I think this at this stage is pretty straightforward. Now let's do a few more interesting things to the flux. Now I basically copy that equation and I write it here. So, the number of atoms per unit area is typically not the best way or most intuitive way that we describe, the fraction of these atoms, right? Because as we showed before, typically we use molar fraction or concentration to describe how many of these interstitial atoms are in the material. So the first thing that we would like to do is to want to convert these numbers into concentration. And the conversion is fairly straightforward because if you think about these N, they're already a kind of a density, but it's the density per unit area, right? And we know that the concentration typically means the density per unit volume, right? So now what you need to do is just to divide this N1, which is already density, but it's a area density, by a distance, right? By a small distance, and convert this to a density with respect to the volume. And that is what we typically call concentration. Now, the distance that you divide this is the separation distance between two successive atomic plane for these interstitials, okay? This particular choice of distance is a little bit arbitrary. For example, you can also choose a half of this, okay? The interstitial, the separation distance, but the key here is to realize that, if you choose this to be a different one, the concentration has also to be normalized with respect to the volume integral. Okay, so this particular choice is natural because it's consistent with the particular lattice structure. Okay, and when you divided this surface density by a distance, you convert everything into a volume density. So this N1 divided by alpha is what we typically know as the concentration of B atom. But this concentration is for this local concentration, right? It's for this very simple thin slab of material, okay, that is along this plane 1 with a very small thickness of alpha. So that's going to be the volume density of atom within this very small within the thin slab. And for following a similar procedure, you can define the concentration for this particular plane, right? You assign this with a particular thickness, and you can have this, okay? So once we define these two concentration, now we can re-express the difference between this surface or area density in terms of the concentration, right? It's a very simple way to derive the relation. Just multiply alpha, which is this, interatomic distance, to the concentration, and you get a difference between the area density, right? And then we plug this back into, we do one more thing, one more trick. So now the difference between these two concentration, okay, when the distance between the plane are very small, which is true in this particular case, because again, alpha is the atomic separation distance between two atomic planes. This is typically very, very small compared to the length scale we're working with in terms of diffusion, okay? So now, given that alpha is very small, you can approximate the difference of the concentration in terms of a constant gradient, right? Of the concentration along this x direction and times alpha. So suppose that because they're very close to one another, you can consider that the difference is just, this is a linear, the linear approximation can give you a very good description of the difference, right? And the difference is literally the height between the two, which equals to slope times the alpha times the distance. So in this way, you convert the concentration difference between two successive atomic plane into the gradient at this particular location and times the distance between these two successive atomic plane alpha. Okay, now after all of these kind of, natural considerations, we can now write down the flux of the atom, the overall flux of the atom from the left to the right in this particular way, right? Because the interesting thing I want to note here is that, if because we're talking about the concentration, if you talk about, if you do the difference, you take the number of atoms or concentration of atoms along plane 1 and minus that of the plane 2, this number should be positive. But because the concentration of plane 2 is smaller than this, right? So we'll take the derivative. The derivative is negative, right? In order to make the whole thing positive, so you have to add a negative sign here. Okay, this basically gives you why this negative sign is inherent here. Okay, so now plugging all this mathematics into our original expression of B, which we derived in this very intuitive way, now we end up with this expression. Okay, so you can now see that the flux of atom B, from left to the right in a particular one direction, okay, is proportional to the minus of a constant. Okay, if for a given material, for a given temperature, okay, this is a constant, proportional to minus of a constant times the gradient of the concentration of that particular atom. Okay, so of course the flux again is the unit of flux is the atom per unit area per unit area per unit time. Okay, so this is the definition of flux. Okay, so now if you take a closer examine of this flux and then introduce a constant for this guy, okay, we call diffusivity. Okay, and typically we use D to denote this, and diffusivity is simply 1/6 times the hopping rate times the atomic distance squared. Okay, so this guy has the unit of meter squared distance squared corresponding to this guy per unit time, because this hopping rate has the unit of per unit time. Okay, so that's the diffusivity. Okay, now if we introduce this constant, and then the flux is going to have a very familiar expression, right? So the flux is proportional to minus of diffusivity times the concentration gradient. Okay, so we call this the Fick's first law of diffusion. Okay, again, I assume that you already seen this, at least the Fick's first law of diffusion, but in a completely different context, like in liquid diffusion. But in here, we derive this for the solid state diffusion. Okay, now the difference between this, so for different systems, as long as the system is diffusive, okay, the flux of that particular diffusing atom is always going to be proportional to the minus of the concentration gradient. The constant of proportionality is also called diffusivity, but the physics contained in diffusivity is quite different. Okay, in a solid state, you see that diffusivity is determined by the atomic interatomic distancing and also the hopping rate. In particular, the hopping rate is very important in describing how fast these atoms can diffuse. And the liquid is quite different. Okay, and the liquid is typically described by the Einstein-Stokes equation, which is proportional to temperature, size of the particle, and also the viscosity of the liquid, right? But in terms of the mathematics and the phenomenological law, they're all described by the Fick's first law. Now, this is the first thing we want to describe. Any questions up to this point? Okay, if not, let's take a closer look at diffusivity. Okay, so now let's examine what are the key differences between solid state diffusion and liquid diffusion. So again, this is a picture that we showed before, and I already mentioned that a key quantity determine the diffusivity of how fast effectively that these particles can move around in one direction is the hopping rate, right? Because as you clearly see, if the particles are doing very, stronger hopping, the chances that it can have a success hop from one location to another will be much higher, and this is going to give you a larger diffusivity, which means they're going to transport faster, right? So the hopping rate is a clearly important factor to keep into account. Now, what are the physics determining the hopping rate? So if we take a closer look at these processes, right? As we said before, suppose this is your diffusing atom, right? It starts from this particular initial location, and once it obtains sufficient large thermal fluctuation, thermal energy, the kinetic energy is large enough so the hop allows this guy to squeeze through this pair of tightly packed atom, get into a new location, right? But once this guy get into a new location, its energy going to decrease like this. So now if we're looking at a schematic plot of the change of the energy, in particular the free energy associated with the diffusing particle, as this particle is doing a hopping, okay, you see that it has to go over a free energy barrier and to get into this particular another new location for the atom, right? So basically you can imagine that this guy is doing this vibration in this valley, and at some particular point, it gets large enough energy to roll over this hill and then get into this local minimum. Okay, that's basically what happens during the hopping. Okay, so we see that the hopping rate is basically proportional to the probability that what is the probability that you can initially at this particular valley and get a sufficient energy to hop over this barrier to get into another valley, right? And this is particularly determining the hopping rate. Okay, now whenever we see some activation energy or energy barrier, that we know this is the right equation to use. Okay, so we use the Boltzmann type of equation. Because this equation typically give you the probability if you have two competing effects, right? And the first one, so first, this is a Boltzmann factor. Okay, I think you will see this a lot of times. And this is the energy barrier. Okay, so basically this is your initial location and this is the top of the hill. And this delta GM is the free energy. Okay, it's not free energy of, you can call it free energy of mixing, but it's basically energy barrier associated with this particular hopping event, right? So you have to receive sufficiently large thermal activation to go over this energy barrier. Okay, so that's the contribution of delta GM. And RT, as we know it, is the average thermal fluctuation that you can get from the environment, right? This is written in terms of the macroscopic unit, and in the atomic unit, this can be written as KT, depending on the unit of your delta G. If the delta G is in joule, you should use RT, but if delta GM is in electrovolts, you can use KT, but doesn't really matter. This RT or KT gives you the average energy scale that you can get from thermal fluctuations for any particular temperature T, right? So these two effects, this is your energy barrier, this is gonna be your kick, right? Large enough to go over the energy barrier. And overall, this Boltzmann factor gives you the probability that when you can receive a sufficiently large kick, sufficiently large amount of thermal energy to go over this barrier. Okay, so altogether, you see that's how the physics come into this picture. Now, clearly, you see the temperature play a role in determining this very important processes, and also what determines this delta GM, the actual material and the particular that this atom that doing the hop, right? So this is the material as a specific aspect of diffusivity. Okay, now what are these two? Okay, so yeah, we already know that this is a free energy barrier, and this V is the vibration frequency. Okay, so the hopping frequency, the hopping rate, and vibration frequency are two different things. Okay, I think you can probably see from here, right? So the vibration refers to, the motion of these particles, the thermal motion of the particles, right? It's vibrating all the time, and only, for example, look at this guy, it's vibrating all the time, right? But after many vibration, it has a one hop, right? So, but again, the more that you vibrate, the higher probability that you can eventually have a hop once this energy from the thermal fluctuation is large enough to go over the energy barrier, right? So the hopping rate is clearly proportional to the vibration frequency of the atom. Okay. Now this Z is the number of available interstitial sites, which also makes sense, right? If you don't have any sites, so all of the sites are already packed. Like look at this guy from the initial condition. That's just a way for, you see, all of these guys they cannot diffuse, they cannot do any hop because all the neighbor sites are already packed, right? By other particles. Only when you have a vacant site can this guy do a hopping, right? So the hopping rate is also proportional to the number of available interstitial sites. Now, all three factors that work together to give you the hopping rate. Okay, so now let's do a little bit more analysis of the free energy barrier. Okay, as we already know, this free energy barrier can be decomposed as a enthalpy component and entropy component, right? Because you place the atom at this position versus you place the atom at this position, they're going to interact differently with these original atom in the system, right? And also the configuration will be different. So you're going to have a different contribution of enthalpy versus entropy, right? If you compare these two different atomic packing configurations. So if we plug in that decomposition of free energy into this difference of enthalpy and entropy into the system, we see a very interesting thing is that the entropy contribution will not depend on the temperature anymore, right? Only the enthalpy contribution characterizing the interaction of this interstitial atom with the original atom in the system in different way going to play a role or work together with temperature. Okay, so and the entropy contribution again, which is fixed given the type of atoms and probably contribution initial concentration, is going to be a temperature independent constant. Okay, so this allows us to write down the diffusivity, okay, into an interesting form, which is composed of temperature independent constant, okay, and a temperature dependent Boltzmann factor. Okay, so and this temperature independent constant are including these terms. This 1/6 inherited from the very simple geometrical consideration. Okay, alpha square again is inherited from the Fick's first law analysis. When we introduce the concentration gradient, we have this interatomic distance, right? And V is from the hopping rate. This is the number of available interstitial sites. V is the vibration frequency, and this is the from the Boltzmann factor, but from the contribution of the entropy part. So the temperature part is cancel one another, so this become a temperature independent constant. Altogether, this contribute to the a temperature independent constant in the diffusivity, and then you have this part which depend on temperature. Now, this decomposition is particularly useful, and that QID is essentially this delta HM, yes, the difference of enthalpy or interaction energy between the interstitial atom in different type of locations, right? That's that. So interesting consequence of this is that if you look at the system, right? If you look at this expression, so the diffusivity the dependence of diffusivity on temperature is typically very important because we need to use that information to design a particular processing condition so that we can have a sufficiently fast phase separation, but we do not want the system to be at too high temperature to minimize some other, undesirable effects such as oxidation or things like that. But if you can see here, diffusivity only determined by the two constant, right, for a given material system. This QID and dB naught, right? So, and these two factor, it turns out that in the experiments can be fairly straightly obtained by doing some experiments of varying temperature. So if you prepare, for example, carbon steel system, and you measure the diffusivity of carbon at different temperature, and when you do that, you can do a log plot of the diffusivity as a function of 1/T. Okay, when you do that, if you do the measure correctly over a certain period of over a certain range of temperature, you see that the diffusivity as the logarithm of diffusivity as a function of 1/T appear to be a straight line, but it's a decreasing line if we do the plot like that. And the slope of this line and versus the intersection of the line with the this 0 point for this axis is going to respectively give you the most two important constant that I'm looking for. And here I just listed some data for typical light interstitial atoms that people have measured. The thing that you can see is that look at one interesting thing that I want to point to your attention is that if you compare this data for D naught and Q, okay, so it's interestingly to see that the hydrogen atom actually have a fairly small D naught, right? This is a temperature independent. You can consider this as a scale, linear scale for the diffusivity. It has a fairly small D naught compared to carbon. Okay, but if you think about it, if I have hydrogen and carbon both diffusing in iron, which atom would diffuse faster based on your tuition?
Carbon.
Hydrogen.
It's only two atoms, either carbon or hydrogen. But based on intuition, which atom would diffuse faster? Hydrogen,
Hydrogen.
right? Because these are
Yeah.
much smaller, right? Much smaller, much lighter atom. So
I have a question. So the D0 is higher for carbon, so it means it diffuses slower, or
no, D0. If so, what D0? Look at the unit and consider the equation that give you as diffusivity or diffusion distance. If you have a distance x t,
okay.
so larger D0 typically means that at least on this linear scale, apparently that carbon has a larger diffusivity,
Yeah.
right? But this is counterintuitive to what we know. So can you tell me why this is the case? What we're missing? So if you compare this, what is Q?
Energy delta H, difference between the two energies.
So basically Q is this is activation energy, right? This is basically the energy barrier that they have to encounter, go over this energy barrier for the hopping to occur, right? Now, if you compare this and this, does that make sense? So the hydrogen atom has a much lower energy barrier compared to the carbon. Does this make sense?
Yeah.
Yes, right? Because hydrogen is much smaller. So, we don't have to work out all the details using DFT, but just use intuition. It's much easier for a smaller atom to squeeze through this tightly packed pair of atoms to get into a new position, right? So it requires much smaller activation energy. And you see that activation energy, okay, is contributed to the diffusivity in an exponential way, right? So that makes sense. So although the D naught for carbon is 1 order of magnitude larger than hydrogen, but it has a much larger Q compared to that for the hydrogen. And this Q basically, the contribution of Q in this diffusivity is exponential. Okay, so at any normal temperature, this factor will be much, much lower. This Boltzmann factor for hydrogen will be much lower, maybe 3 magnitude lower, than that for the carbon. So overall, the diffusivity of hydrogen will still be lower. Okay, does that make sense to everyone? Okay, so so that's basically all I want to say about Fick's first law. Again, we derive the general equation for the flux, right? I think these two summarize what we already derived. This is the very simple relation between flux and the concentration gradient, right? But in a solid state, we know that this diffusivity, which is a proportionality constant, contains very interesting physics. So we spent some time to look at what information is encoded here, and we derive this equation, which tells us that this diffusivity sensitivity depend on temperature, right? Through the Boltzmann factor, and then there's a temperature independent constant related to the material structure and also some aspect of the enthalpy of mixing of the system. And this diffusivity is totally accessible. Diffusivity and the temperature dependence is totally accessible via experiments. Okay, so that's Fick's first law. Okay, now knowing this first law is great. At least we have some mathematical rule to quantify the flux in the system. If you know the diffusivity, you know the material, you know the initial concentration, you can compute the flux, right, of the atom. But what we're more interested in is a closed set of equation that allows us to know the distribution of concentration at all times, right? But knowing flux alone is not sufficient for us to do that. So we need to look for another equation that can close the loop. Okay, so this equation is even less dependent on material system or on what state you're looking at, right? It doesn't really matter whether it's a liquid state or solid state. It's based on the continuity equation, or sometimes called the local conservation equation. Okay, so now we're going to quickly show how we're going to get this. So suppose now that you can consider that we still have that trunk of solid material, but we only look at a very thin slab of that material. And I didn't show anything within this, just to imagine that you have some material in between, right? So now what I'm interested in is that I'm interested in, what is the rate of change of a concentration within this very local volume, okay, per unit time due to flux, right? Because I know I'm only again interested in one direction, so I know on the left side of this volume there will be a flux come in, and on the right side there will be a flux come out. And by this flux, I already mean the overall flux, right? It's already taken into account atomic transfer, atomic hopping from both directions. So I'm talking about overall flux. So I only need to keep track of one direction. But looking at, this is the plane that they get in, and this is the plane get out, right? So now this is, I'm interested in that over time tau. So if the t is my initial time, I'm interested in what is the change of concentration within this box, okay, during time tau, starting from time at t. So this C, which is the concentration of the within this small box at time t plus tau, right? This is my concentration after certain time tau. And this is my initial concentration, C at time t, right? I take the difference, I divided this by tau, okay? I get the rate of change of the concentration in that small volume, right? Does this make sense? And what are the causes for this change of concentration over this time tau? The only
concentration gradient.
The only cause for the change of the concentration is the flux, right? Because I have some extra atom come in from the left of the box of the volume, and I have some atom leaving this particular box from the right, right? So the flux is the only reason, the only cause that leads to the change of the concentration. So now, what is the flux? If you write down this again in terms of flux, right? So we know flux is what? Flux is the number of atoms that getting into the box minus the number of atoms get out of the box. But don't forget, flux is per unit area, per unit time, right? So I have to time A, which is area, and times the time tau. That is the total number of atoms that get into the box. Overall number of atoms get into the box during this time tau. Does this make sense to everyone? Okay, and then I have to convert this to the concentration, right? So this is a number. How can I convert a number to the concentration? I divide the volume, right? A is area, and delta X, which is a very thin, a small thickness of the box, but altogether this is going to give you the volume, right? So I have the number. This is a change of number of particles, okay? And then in the volume, so what do I have here? This is the total change of concentration, right? And if now I divide it by tau, I get the rate of change of concentration, right? And I know that this is only cause for this guy, and I express these two in the basically they're same. I already expressed everything in the same footing, so I can simply I can simplify this a little bit, okay? And then I can let this two equals to one another, like this guy, okay, equals to this guy, okay? But if you look at that, if we take the limit, the tau is very, very small, okay? What do you call this? This is a small change over a small period of time. This is a partial derivative of your concentration with respect to time. Does this make sense? Because this is the rate of change of a concentration at time t, right? So this is simply given by this guy. Now, what is this? You have the flux at x plus dot x minus the flux at x and divided by dot x, and take dot x goes to 0. What do you have here?
A differential with respect to distance.
Exactly. This is the gradient of your flux, right, at x. Okay, and we know that these two equals to one another, and this equality holds even in this limit. Okay, so in this way, you derive the so-called continuity equation or the Fick's second law. Does this make sense to everyone? Okay, so you can easily generalize the 3 dimensions, which I wouldn't do here. I will just stick to the 1D, and if you're interested, you can try to generalize the 3 dimension as an optional homework. Okay, so now if I collect Fick's first law and the Fick's second law, you'll see what do I have. So this is a Fick's, we just tidy up this a little bit. This is a Fick's second law, or sometimes called derivation equation or continuity equation. It simply tells you that, if there's no flux or there's no source of sinks, the only reason that caused the flux, the only reason that caused the concentration to change over time is due to flux. Okay, so no solutes are created, no solutes are being destroyed. So everything is conserved. And then the only possible way that can change the concentration within a unit volume is due to the flux. Okay, so that's what this means. Now, if we combine these together, okay, so this is the Fick's second law that we derive altogether, right? And this is the Fick's first law. What happens if you combine these two together, for example, by plugging in this expression for the flux into the Fick's second law? If you replace this J with this JB and this expression, what do you have?
Heat equation.
Okay, you have a partial differential equation, which is which contains only one variable, right? Or field variable as the concentration field, right? So basically, if you take this, you plug this back in here, and we consider diffusivity is not changing with location. It changes with temperature, it changes with material, but it does not change with location, right? For a given material. So in terms of differentiation with respect to x, it's a constant. So we can get this guy out, and the two negative sign cancels one another, right? And then you have a partial derivative with x once, and then if you have another partial derivative, you have the second order derivative with respect to x. Does that make sense to everyone? So this is the diffusion equation in a one-dimensional case. Okay, but you can see that this is nothing more than just combining the Fick's first law with Fick's second law. Okay, so this is the
Professor,
diffusion. Yes.
in 3D, it's not independent, like in X and Y and Z direction, right?
Each direction is still independent.
Uh,
The overall
why?
concentration, because the flux are independent of one another, right? You're doing the random hops, and we consider this is a very low concentration limit. So the atoms are hopping randomly in each direction. So all of the concentration along each direction is independent, but you have to generalize this operator Laplacian to 3D. So instead of having only partial square c with respect to partial x square, you have partial square c, partial x square plus partial square c, partial y square, partial square c, partial z square. So this is 3D Laplacian, but the contribution from each direction is still independent of one another, as a matter of fact.
So can we also call this as a heat equation? Like it's it's similar, right?
This is a Poisson's equation in general. It can apply to heat diffusion, it can apply to mass diffusion, it can apply to any type of diffusion you want.
Okay.
But it's characterized diffusive transport in general. Okay.
Okay, Professor.
Are we good? So the exact thing that I want to mention is, yes. So I think I will stop here for this class because I want to reserve some time for the homework, because I did get a lot of questions. So yes, so that's pretty much all I want to say for this particular class. And we talk about interstitial diffusion as a particular example of solid state diffusion to work out the Fick's laws, right? And we derive Fick's first law, derive Fick's second law together, and from the Fick's first law, we analyze diffusivity, which is a very important parameter characterizing diffusive transport, and we see that there are very interesting physics related to solid state, right? This is related to the hopping rate, related to the vibration frequency, atomic structure versus the interatomic distance, and the coordination number. And more importantly, diffusivity is very sensitive to temperature through this activation energy barrier. Okay, and finally we derive diffusion equation together. And in the next lecture, we're gonna solve diffusion equation using different techniques. Probably gonna take 2 lectures for this. And finally, we're gonna show that this diffusion equation we derived for mass transport is also, has a very close mathematical analogy to all different type of diffusive transport, including heat equation. So that's what we're gonna do in the next lecture. Okay, but for today, we're done for the new material. Any questions? Okay, good. I think this is a simple lecture because we already know most of the stuff that I'm talking here. So I do want to quickly go through the homework. Okay, so can you see my homework? See the Word document for the homework?
Yes.
Yes.
Okay, good. So just for your information, I did actually post a very short going through lecture for the homework. but I don't know whether you have a chance to look at that or not. But nonetheless, I still get a lot of questions, in particular to number 5 and probably number 6. Okay, so I just want to use extra time to quickly go through this together. So hopefully this will clear any doubts. So I think the majority of the question I have for this is that, in the class, we describe in general how you would like to construct the phase diagram, right? And typically you're working with 2 different phases, like a liquid or solid, or 2 different solid phases. And in those cases, you can easily construct the, use the, for example, the double tangent construction. If you have 2 free energy curves, one is solid, the other one is liquid, and then you can use double tangent construction. This is very bad drawing, but you get an idea, right? For this, the most question I get is that this is a single free energy curve, and it's in a very kind of strange way, quite different from both the ideal solution or regular solution energy. Now, how we could do this? Well, the idea is very similar. Okay, so first, I think this is a reasonable question because it shows you that in general, as I emphasized many times in the class, that regular solution, even though this is the best model that we described in the class, is not going to be applied to any real solution. So again, this is a better model, but it's still not the best model. But you can see that the form of free energy is already very complicated. Okay, so and if you want to still try to identify different contributions, okay, so now I can point out to some of the traits. So if you look at this, okay, first, again, it's given in the form of normalized, right? So we have a free energy, but we're not interested in the actual absolute energy scale. So we normalize everything with respect to the free energy of pure A, right? Now, if I tell you that, okay, this is the contribution that we typically call G1, if you still know what that is.
It's G1, the initial.
Yes, this is typically what we call G1, okay? This is a contribution from G1, and this, all the remaining part is the delta G mix. I just use delta GM. Okay. So does this make sense to everyone? If you want to try to make a connection to what we learned, okay? Now let's look at this G1 part. I normalize the overall free energy with the free energy of pure A. So now if I ask you, okay, what is the free energy of pure B in terms of pure A? What is going to be that number?
0.9.
0.9.
0.9 times GA, right? Does it make sense to everyone? So again, it's depending on the free energy of both systems, but I simply normalize the numbers, right, with respect to a particularly selected energy scale. But this is basically GB pure for pure B, right? Molar free energy for pure B, but measured with respect to the molar free energy of pure A. Nothing else than that, okay? But we still have contribution from both A and B, and that is the G1 part, okay? And now if you want to see this, okay, and this part is the, this part is the contribution from the mixing, right? As we already know. But is this the only contribution from the mixing, from the delta H mix? Or let me ask you this way, if I give you a free energy like that, I ask you to decompose the contribution in the free energy of mixing, tell me which part come from the mixing of enthalpy and tell me which part come from the mixing of entropy. How would you do that? Which is the key that tells you, which part is from which?
The omega term is coming from enthalpy and the rest T0 minus T term, the whole plus is coming from entropy.
How about this term?
That term would be coming from enthalpy as well because there's no temperature associated with it.
Exactly. So, in general, the way to describe which term come from entropy and enthalpy gonna be C, or in general, you get this information from whether this term is associated with the temperature, right? Because we know, we know this is true for all the time. This is delta H minus what? T times delta S.
Professor, then there's another term, right? If you it's like 1 into XA into XB from the middle term. It's independent of temperature. The middle part.
Which part?
T naught minus T upon T naught. If you cancel T naught and T naught.
No, this is temperature dependent. I just measure with respect to a particular scale, but it still is temperature dependent.
T naught is a constant, right?
T naught is constant for this particular choice, but it's a scale, right? This is, you measure this with respect to a scale, but the whole thing is dependent on temperature, right?
Yeah, so if you take only, like if you divide the above numerator with denominator is 1 minus T. So the first part is 1 into XA into XB, which is not dependent on T. Only minus T XA XB
No,
is...
the contribution altogether, because the T dependence does not by itself specify this particular system, right? It's the difference from T naught measures the contribution of entropy in this case, right? Because in this case, what is your T naught? Like in our particular, in the regular solution, what is your T naught?
It's the any reference temperature.
No. It's absolute zero. So you don't have exact T naught, right? That makes sense. So because this T is in absolute scale, but it measures a difference. So when this entropy have no contribution, it has no contribution at T equals to what?
0.
Exactly.
No.
And in here, when it has no contribution, at T equals to T naught, you can basically imagine that, right? Because then this is going to be a temperature independent thing, right? Does that make sense?
Yeah.
So this is basically, again, I'm not asking all these questions in the homework, but in general, if you think a little bit, this would be how we interpret this, right? So it's a very complex system that is quite different from what we described, but that is reality, right? Because I don't know what you're working on in terms of research, and there's certainly no guarantee that all of the system that you want to study can be described by a regular solution or ideal solution. So you can try to rationalize what you see in the future in your study. Okay, but anyway, so this is like just one example that promotes you to think a little bit more, right? To go beyond what we learn in the class and be able to apply them to a different system. Anyway, so that's that, right? And then once, again, but that is not quite essential to what we're asking here. So the key I'm asking is that by considering this free energy at different temperature in the range of this, you can definitely consider more if you have time or your computer is fast, and determine the corresponding phase diagram of the system using the method we discussed in the class, namely the double tangent construction. Okay, so now the question I have is that most of the cases that, okay, this is a single free energy curve, right? Now, in order to construct the phase diagram, you need two free energy curves. Now, how can you do this with a single curve? Well, so if you do the free energy plot, this is true, we have a single curve, right? But think about the ideal a regular solution, right? At low temperature, what do you have for the overall free energy of the regular solution? If you still remember, you're gonna have something like that, right? So this is gonna be pure A, this is gonna be pure B, right? So although it's still a single curve, which means that, okay, you still have a single solid solution with the same crystal structure, but clearly it will develop if you do the plot correctly, by having sufficient number of points along the composition axis. You will see two, I will not say very clearly, but at least the two well-defined local minimum, okay, at low temperature, at least at T equals to 1000 K, because I've done this before, so I know that at this temperature you will see local minimum, something like this. Okay, and this is a single curve, right? But you see it has two local minimum. And what do we call these two faces? This is my alpha prime, and this is my alpha double prime. Okay, so you have a single curve, but at sufficient low temperature, we'll see two local minimum. And then you're going to do the double tangent construction with respect to this two local minimum. Okay, and you're going to find a different composition for alpha prime and alpha 2 prime. And what we do is that following the same way that we did before, you're going to choose your temperature axis. You're going to label these 2 points. As you lower the temperature, you'll see that these two local minimums can get wider and wider. Okay, so eventually you're going to get something like that. All right, and then when you connect these dots together, you should be able to have a free energy curve.
Professor, I still don't understand why, if I'm getting a positive G, the phase is stable. I'm getting positive G for all these plots.
Why the phase cannot be stable with positive G?
Yeah.
No,
Why is it in the phase diagram?
no, the question that why a phase cannot be stable with positive G. Now, let me give you two phase, right?
There should be something to compare, like there can be more phases which are stable than the positive G phase, right?
No, for this particular problem, positive G phase is the same. The first one is that in here we're not talking about the stability of, if you compare what we're comparing, it's not the absolute value of the phase. So you have to understand what we're comparing here, right? We have two systems. Now tell me what are the two candidates you're comparing here?
Temperature and composition.
No. We're comparing the phases, right? It's like you have a liquid phase, you have a solid phase. You're comparing the stability with respect to this two, right? And in the coexistence, you're comparing the stability of a single phase versus the coexistence of two phases. Now tell me what you're comparing here.
The separation of alpha to alpha plus alpha prime to
exactly.
alpha double prime.
So what are the phases? What are the two systems?
Alpha and alpha dash plus alpha double dash.
Exactly.
Yeah, I get it, but in real, will it happen? Because this has a positive G.
Again, what's the problem with positive G? Your positive G is determined by this, right? I have, the molar free energy itself depending on a choosing point, because this is the free energy have enthalpy or has a entropy contribution. So it's a potential energy in particular. So it depends on the reference, right? If my GA is super positive and my GB is super positive, it doesn't really matter what's your free energy of mixing. You can always get positive numbers. So that's really matter because that's the reality. You're working with these two alloy, and for the most stable cases of A and B, they're positive. So
and there can be metastable phases. These are.
No. There's no metastability of any issue. So in here, so the value of the free energy, whether it's positive, whether it's negative, is not an issue here. At least it's not an issue that you should consider for this particular problem. The key here is to compare the stability of alpha versus alpha plus alpha prime, right?
Okay.
Right, and whichever of these two choices is going to have a lower free energy will be the stable phase. Their absolute value of their free energy is not really an issue here. We're comparing these two. They can be both positive, but I know when alpha prime plus alpha double prime is lower, this means my system favors this two-phase coexistence. Otherwise, it favors to exist in a single phase as alpha, right? So the absolute value of free energy is not a concern here because it tells nothing about stability of these different choices. And a system can definitely have a positive free energy, but still to be the most stable system, right?
Yeah, we have to give energy.
Well, think about the plasma in the sun, in the core of the sun. It's a stable thing, you see this, but it's in a high temperature plasma state. The free energy, I guarantee you, is positive, but it's stable. It exists in nature.
Yeah, entropy is too high. Okay.
Yep. So yeah, that's what, right? So the key here, I think, is you have to resolve this curve along the x composition line carefully, so that you see these two local minimum. If you just choose 10 points, I don't think you can precisely see this local minimum. I think if you choose 1,000 points, it's good enough to see this local minimum. And for the double tangent construction, you can either do this numerically, by literally checking the tangent at each point along this particular curve and do a numerical comparison when they equals to one another or very close to one another, or you can do this analytically by solving the equation. But I think analytical solution is a little bit challenging here, but I think it's doable. Okay.
Professor, how correct do you want it? Like, can I round up the values?
Yeah, sure. To the best you want, to the best you think is appropriate. Suppose this is a research problem. No one tells you what is the correct thing, and you need to determine what is the best that you can offer for this case. Okay.
Okay.
Can I ask
Yeah.
a quick question?
Sure. So let me first finish this, and then we can go to the questions. This still is being recorded as part of the lecture, so let me quickly finish this.
Okay.
Yeah, that's the point. This point have any special significance? And if you do this correctly, you'll see that this point is going to be the highest point you see on the phase diagram. Okay, it's roughly here. Okay, so and I'll leave the significance part to you. Okay, so what is the significance of this particular point? That for question 5, I think this is the problem that I have most question for. Okay, let me clear all. I think this is clear, right? Let me see. Yeah, and for question 6, I think the only thing I'm missing here is that I forgot to put in this plot initially, but I added it back. So I think this is going to clear any possible doubts, right? The question is pretty straightforward. If you follow these steps, I think it's quite easy to show what we're looking for at the end. Okay, so now I already used all the time. Apologize for the 2 extra minutes that so I'm going to stop sharing. I'm going to stop recording. Okay.